In this video, we're going to talk about double integrals over general regions. So, as an example here, let's look at the double integral over R, where R is this shaded region here, of x minus y dA. Now, certainly, R is not a rectangle. However, we can attack it much like what we did with the problems where we did have double integrals over rectangles, because we can describe this region in terms of bounding functions. What I mean by that is, if we hold x constant for a particular x value, then we know that the y value ranges between that x squared and 4. And this is true for any x value that we pick between 0 and 2, so we can express the region R as the set of all ordered pairs such that x is between 0 and 2, and the y is between x squared and 4. So now we'll use that information to help us write the double integral as an iterated integral. Now, it does matter the order here. Unlike for rectangles where we didn't really matter the order does matter here. Because remember, this is a double integral. It needs to be a number when we're done. So our outside integral cannot have variables in the limits of integration. Okay, so since the y is written in terms of the x, that tells us that the y has to be the inner variable that we're going to integrate with respect to. So here we'll get the integral from 0 to 2, integral from x squared to 4 of x minus y dy dx. And then we proceed just like what we did with double integrals over rectangles. Take an antiderivative with respect to y. We have endpoints here of x squared and 4. We'll plug those in for the y's, just like we would in previous problems. We'll just have an x squared to plug in for y when we do the second one. Now we have a function of x. Anti-differentiate from 0 to 2, or excuse me, anti-differentiate and then plug in the 0 and the 2, and get negative 44 over 5 as our final value. Let's look at another example. Say we have the double integral of x over y to the 7th plus 1, where our region is for x is between 0 and 8, and the y is between the cube root of x and 2. If we look at a graph of this, here is y equals cube root of x. Here's y equals 2. So the shaded region is the region that we're interested in. Now, even though the y is given to us in terms of x, which would suggest that we want to integrate with respect to y first, this function is very, very difficult to integrate with respect to y first. You'd have to factor and use partial fractions if possible. It's just a mess. You don't really want to integrate this with respect to y first. Okay? So we would much rather integrate with respect to x first because that's a much simpler function to integrate first. Now again, if we're going to integrate with respect to x first, we need limits that are in terms of y. We can't have cube root of x that is an outer limit of integration because we need to end up with a number when we're done. Okay, so we'll have to switch our bounding curves around. Certainly the left curve here is x equal to 0. If we solve the right one for x, getting it in terms of y, we'll get x equals y cubed. Okay, so then we'll have that for a fixed y, the x's go from 0 to y cubed, and then the bounds for y will be 0 to 2. So integrate with respect to x first, the bounds are 0 to y cubed, then integrate with respect to y, the bounds are 0 to 2. Again, this is a much simpler antiderivative to do. Get x squared over 2. The y to the 7th plus 1 again is a constant. Plug in your limits for x's. You'll get y to the 6th over 2 times y to the 7th plus 1. This is now a u substitution. We can take the 2 out in front, and we'll need to adjust with a 1/7 for that 7 for the du. We'll get 1/14 log of absolute value of y to the 7th plus 1. Plug in your endpoints, and you get 1/14 natural log of 129. Let's do another example here. Let's do the double integral of y cubed, where r is the parallelogram given with those vertices. So let's start with a graph first. Notice again, we do not want to integrate this with respect to y first, because with respect to y, again, we hold x constant and look at the bounding curves for the in terms of x for the y's. Well, here we would go from the x-axis to that slanted line, but from 3 to 4, we go between the x-axis and that horizontal line, and then from 4 to 7, from this slanted line to that horizontal line. So you'd have to do 3 separate integrals if you chose to integrate with respect to y first. That would be difficult. Okay? So even though this is easy to integrate with respect to x or y first, unlike the previous problem, we're going to determine the order of integration based on the region, and the region is telling us to integrate with respect to x first instead of the y. Okay? So this is exactly what I mentioned. If we try to integrate with respect to y first, we notice that those bounding curves in terms of x change as we move from left to right. So instead we'll integrate with respect to x first. Here's a left bounding curve, here's a right bounding curve. In terms of y, solving that for x, you'll get x equals 3/4 y, or over here we'll get x equals 3/4 y plus 4. And certainly we see that the y's go from 0 to 4 in that case. So now, set up your double integral. Here is your inner with respect to x, inner integral with respect to x. Here are your bounds in terms of y. Find an antiderivative. Notice it's just x times y cubed. Plug in your endpoints for x and simplify. You'll just get 4y cubed. Here we get y to the 4th. And then we get 256 for our final answer. Let's do one more. Here is, we want to give you an iterated integral and ask you to find it. The issue with this one is that if you try to find the integral as written, it's impossible to find an antiderivative for e to the y squared in closed form. So literally, we can't do the problem as written. So instead, we're going to reverse the order of integration. All right, so the first thing we'll do when we reverse the order of integration is look at the region that we're integrating over and see how to rewrite it. Okay, so here is the line y equals x. Here's the line y equals 1. Those are your inside bounds. And your x goes from 0 to 1. So since it says it's between x and 1, I would shade this region up here. So this is the region that we're going to integrate over. Now let's flip the order. Let's integrate with respect to x first, holding y constant. Okay, that means we need bounding terms in terms of y. Well, here's x equal to 0, and this is x equal to y. So you see that your x is between 0 and y, and then your y's go from 0 to 1. So now reversing the order of integration, we have integral from 0 to y of e to the y squared dx dy. This now is easy to integrate with respect to x. It's just x times e to the y squared. Plug in your limits, and now you've got y e to the y squared. Notice it's got that missing factor that we needed to find that antiderivative. That's a simple u substitution, and then plug in your values for y to get your final answer.